Hello and welcome to today's episode of Bales Chemistry. Today we're looking at enthalpy changes in combustion, how we can measure that in the lab and how we can collect the data and what we do with it once we've got it. This is going to appear on paper 1 and 2 of your AQA exams and it's specification 1.4 energetics. So last episode we looked at measuring the enthalpy changes of a reaction involving a solution, and that's where the solution absorbs the heat of the reaction and therefore we can talk about the solution being in the surroundings. Now today we're going to look at the combustion reaction which releases heat and can heat up the water. The water now is going to be the surroundings. That's quite an important distinction that we're going to make today. So if we remind ourselves of that equation that we looked at last time, we looked at energy transfer equals mass multiplied by specific heat capacity multiplied by the change in temperature, often simplified down into Q equals MC delta T. Couple of little things to watch out for. The Q here needs to be in joules, and then we need to convert that into kilojoules for our final answer. Our M in this case today is going to be the mass of the water that we're heating up. The specific heat capacity is going to be 4.18 because we're heating up water, and delta T needs to be in Kelvin. But don't forget that 1 degree Celsius equals 1 Kelvin, so we don't need to do any energy conversions there because it's a change in. So now we've got our energy transfers calculated, we need to remember that enthalpy changes are per 1 mole of reactant, so we need to work out the number of moles of fuel that we've burnt. Once we've got that, we're going to use the equation minus Q over N to work out the enthalpy change. So we'll look at a simple example to put these equations into practice. We'll take 0.9 grams of ethanol that was burnt, raising the temperature of 150 grams of water by 20 degrees Celsius. So we'll start off by calculating the energy transferred. We'll use Q equals MC delta T for that. We'll put the numbers in, remembering it's 150 grams of water that we want to put in here, not the 0.9 grams of ethanol. We're going to multiply that by 4.18, the specific heat capacity of water, and multiply that by 20 degrees Celsius or 20 Kelvin, which is how much energy has been transferred to that water. And that gives us an answer of 12,540 joules. In the next step, we'll just quickly convert that to kilojoules. So we'll have 12.5 kilojoules. So the next thing we need to do is we need to work out the moles of fuel burnt. So to do that, we'll use the equation number of moles equals mass divided by MR, and we'll plug the numbers in. So we've got 0.9 grams of fuel burnt divided by 46, which is the MR for ethanol, and that gives us an answer of 0.02 moles. The final step of this equation then is to work out the enthalpy change, and that's where we use our equation minus Q over N. We'll plug our numbers in, and we'll get an answer of minus 625 kilojoules per mole. Now, does that sound about right? Well, we know it's a negative value, which means it's an exothermic reaction, and combustion is an exothermic process, so it looks like it's along the right lines. So to make sure you always get your calculations right, there's 3 easy steps to remember. The first step is to work out the energy change or the energy transferred using Q equals MC delta T. In this case, it's really important that we remember that the mass here, the mass is the mass of the water. Okay, in the second step, we need to remember that we need to calculate the moles of the fuel burnt this time. This is different to last time where we looked at the limiting reagent of the chemical reaction. And in the final step, just like before, we do minus Q divided by N to get the enthalpy change for the reaction. I hope you've enjoyed today's video. If you have, please hit the thumbs up below. And for more exciting and interesting content about A-level chemistry, make sure you hit the subscribe button. Thanks and have a great day.